Welcome to this rigorous exploration of granular physics, where we'll discover why sand behaves as both solid and liquid. Here we see granular matter, discrete solid particles that collectively exhibit fascinating emergent behavior. Let's begin by understanding what fundamentally distinguishes granular materials from ordinary solids and liquids. Granular materials occupy a unique regime, macroscopic particles where thermal energy is negligible, unlike molecular fluids. The thermal energy kBT is orders of magnitude smaller than gravitational potential energy mgd for millimeter-scale grains. Interactions occur through direct mechanical contact, normal forces, friction, and collisions, not thermal fluctuations. The key to understanding granular solidity lies in force chains, a remarkable emergent structure. When you apply load to a granular pile, stress propagates through linear chains of particles in contact, shown here in red. The stress tensor is computed from contact forces F and branch vectors R connecting grain centers across all contacts C. Force chains form quasi-linear paths from loading point to boundaries, creating an inhomogeneous stress distribution. Let's ask, why do forces organize into linear chains rather than spreading uniformly through the material? The answer lies in Hertzian contact mechanics. Normal force scales as overlap to the 3/2 power, creating geometric nonlinearity. A linear chain transmits force efficiently with minimal deformation, while diffuse spreading requires more elastic energy. Now we encounter one of the most profound concepts in granular physics, the jamming transition. Below a critical packing fraction, grains flow freely. Above it, they form a rigid, stress-bearing network. The critical packing fraction phi c marks a sharp transition from fluid to solid behavior. The shear modulus G jumps discontinuously at phi c, demonstrating the transition is a critical phenomenon. Near jamming, the shear modulus scales as phi minus phi c to the power beta, with beta approximately 1/2. The coordination number Z, the average contacts per grain, is the order parameter for jamming. At the jamming point, Z equals 2D, the isostatic value where constraints exactly balance degrees of freedom. Friction between grains fundamentally determines when a granular solid begins to flow. Friction force FF opposes sliding, bounded by the Coulomb criterion. FF less than or equal to mu times Fn. The coefficient of friction mu, typically 0.5 for sand, sets the threshold for motion. A pile of grains forms a slope. The maximum stable angle theta is the angle of repose. The angle of repose theta r satisfies tangent theta r equals mu, directly linking microscopic friction to macroscopic geometry. This connects to the Mohr-Coulomb failure criterion from continuum mechanics. How do they relate? The Mohr-Coulomb criterion states shear stress tau equals cohesion C plus normal stress sigma times tangent of internal friction angle phi. For cohesionless granular materials, C equals 0, and phi corresponds to the microscopic friction coefficient. When we continuously add grains to a pile, avalanches emerge as a spontaneous dissipation mechanism. Adding a single grain can trigger an avalanche where many grains suddenly flow, relaxing the slope angle. The angle oscillates between theta max and theta min, with avalanches occurring when theta exceeds the maximum stable angle. Remarkably, avalanche sizes follow a power law. Probability of size S scales as S to the minus tau, with tau approximately 1.2. On log-log axes, this appears as a straight line with slope minus tau, indicating scale-free behavior. This exemplifies self-organized criticality, where the system spontaneously reaches a critical state without tuning parameters. Now we explore how mechanical vibration can transform a jammed granular solid into a flowing fluid. When we vibrate a container vertically with amplitude A and frequency omega, grains begin to flow and rearrange. What dimensionless parameter determines when vibration induces fluid-like flow? The answer is gamma, the dimensionless acceleration, A omega squared divided by G, the ratio of peak acceleration to gravity. When gamma exceeds 1, grains separate from the container floor during downward acceleration, entering ballistic flight. For gamma greater than 1, grains detach and the effective confining pressure drops, allowing rearrangement. The packing fraction decreases with gamma, showing a transition from jammed to fluid behavior near gamma equals 1. In the strongly vibrated regime, we can define an effective temperature describing granular agitation. At high gamma, grains collide inelastically like molecules in a gas, with random velocities characterized by temperature. The effective temperature is defined from the mean square velocity, m times versus squared averaged, divided by 2 kb. This effective temperature scales as a omega squared, the square of the vibration velocity amplitude. Collisions are inelastic with coefficient of restitution E less than 1, dissipating energy that vibration continuously replenishes. The restitution coefficient E, the ratio of relative velocities after and before collision, is less than unity. Let's perform a quantitative estimate to connect microscopic and macroscopic scales. Consider typical sand. Grain diameter 0.5 millimeter, material density 2,500 kilograms per cubic meter. The grain mass is rho pi d cubed over 6, approximately 1.6 times 10 to the minus 7 kilograms. Now estimate the force in a chain supporting 10 centimeters height of sand. The pressure is bulk density times g times h, about 60% of grain density times g times height, giving 1,500 pascals. Each contact area scales as d squared, about 2.5 times 10 to the minus 7 square meters. The force per contact is pressure times contact area, approximately 4 times 10 to the minus 4 newtons. This force is about 250 times the grain weight, showing chains support large stress concentrations. An essential feature of dense granular flow is dilatancy, volume expansion during shear. In a close-packed configuration, grains must push apart vertically to slide past each other horizontally. The material dilates, increasing its volume fraction, creating a coupling between shear and normal stresses. The volumetric strain rate epsilon dot v is proportional to shear rate gamma dot, with proportionality constant beta, the dilatancy angle. Dilatancy explains why wet sand is firm. Water in pores creates negative capillary pressure resisting dilation. Capillary pressure P cap equals 2 gamma L versus divided by R, where gamma LV is the liquid vapor surface tension and R is the pore radius.